not fully controllable. So let me recap so that we start, since I think I was going a little bit fast on Monday. Any questions before? Okay. So what we basically did is we said, okay, let's start considering a system S governed by the usual equations, x dot equal ax plus bu. And we recalled the concepts of controllability of eigen values and natural modes. And finally, we defined a matrix P if X is an n-dimensional vector. We define this matrix AN-1B, which is for the CISO system, n by n matrix, and we defined it as a controllability. And so we obtained a result which states P non-singular and this is equivalent to all the natural modes are controllable. And from a first perspective, this meant that if we apply an impulse input, then we would see in the state impulse response all the natural modes of our system. And we also gave a different interpretation of this controllability as the existence of an input which is able to transfer the state from any initial state to any finite state in finite time and in a time interval which we could decide. So this is really a state is controllable to another state, or a state is reachable from another state. These two concepts are equivalent for this class of systems we are considering. So sometimes you will hear reachability, sometimes you will hear controllability. These are the same concepts. It's just the point of view, controllable to, reachable from. Okay. And we then studied the more interesting case in which there exists some hidden dynamics. For example, this happens when P is singular. Why am I connecting these two concepts? Because when P is singular, we found a change of coordinates such that in the new coordinate, we had a very special structure of the original system, which is a decomposition with respect to the controllability property. And so we were able to distinguish two subsystems, S1 and S2. The output could depend on both states. System Z1 depends on the state Z1, system S2 on the state Z2. And we had that the state of S2 could influence the state of S1, but not vice versa. And in a matrix form, this means that in the new coordinates, we had a very special structure of the dynamic matrix, which we found to be A11, A12, 0, A22, and also a very special form of the matrix B in the new coordinates. And these dimensions were M and the rest n minus m, where m is equal to the rank of the controllability matrix. So this decomposition here clearly shows that S1 is governed by the matrix, dynamic matrix A11, and has state Z1, which is m-dimensional. S2 has dynamic matrix A22. The state is Z2 and has n minus m components. We understood that S1 is controllable, which is equivalent to saying that the pair A11 tilde B1 tilde is controllable, or the corresponding controllability matrix, which is an m-dimensional square matrix, is non-singular. But more interestingly, we also understood that S2 is not controllable, but let's say in the worst situation, in the sense that none of its natural modes is controllable. So this is the origin of one potential origin, as we saw when we studied the natural modes of hidden dynamics. One of the two potential creation of the hidden dynamics. So this subsystem here is really something that influences the output or may influence the output either directly or through the system S1, but its dynamics cannot be altered. Its time evolution cannot be altered by any direct through the input U or indirect through the state of S1 cannot be changed or influenced. So it only depends on the initial condition of the state Z2. So in the new coordinates, we had Z, Z1, and Z2 with the dimensions that we defined previously. And well, this gives really an inside vision of what can be achieved and what cannot be achieved. In particular, we found very interesting result that if S is controllable, so P is invertible, we can arbitrarily assign all the eigenvalues to the closed loop system obtained through state feedback. So we started looking at this very special situation in which the whole state is available. And in which we have the possibility to measure. So this whole state, X, and close what we defined as a state feedback, which is something different from what we have been doing previously, in which we were closing a feedback from the output. And so either we do directly this, or we may even have an extra input for solving some other problems. So this is a state feedback. You see, we are not feeding back the output, but the state. And through a set of algebraic relationships and results, we found that in order to assign lambda 1 desired up to lambda n desired, so if these are the desired closed loop eigenvalues, then through the Ackermann formula, we found out that the matrix of constant element F, which assigns these desired eigenvalues, was minus gamma P desired A, where gamma is the last row of the inverse of the controllability matrix, and P star lambda is the desired closed loop characteristic polynomial. Which we should evaluate in the matrix A of the open loop system. So there's a very simple and straightforward formula that we can, no, that's not what I like to obtain, a nice, okay. And so this formula is absolutely straightforward to use. Then we said, okay, what happens if S is not fully controllable? Well, if we look at this decomposition here, which I'm going to rewrite, we found out that in the new coordinates, U equal F tilde Z, we set the new coordinates, we would have obtained a closed loop dynamic matrix, which is of the form A11 tilde plus B1 tilde F1 tilde zero. Whatever is here, we do not care, and here A22 tilde, where F tilde is decomposed as F1 tilde and F2 tilde, which we see has no effect on the closed loop eigenvalues. So we can easily set this to 0. By doing this computation, we again understood that the eigenvalues or the dynamics of the uncontrollable subsystems cannot be modified. While since A11, B1 tilde is controllable, for sure, there exists F1 tilde such that the eigenvalues, let me write explicitly, of A11 tilde plus B1 tilde F1 tilde can be assigned, but of course these are just a number which is not n, but which is n. So we can assign only the eigenvalues to the controllable subsystem. So this, in some sense, also is telling us by studying this controllability property, what can be achieved and what cannot be achieved. So let's now take some examples so that we fix this idea. So we saw as a first example, Monday, this system here, in which we studied the controllability matrix. So P is BAB, and it's 1 minus 1 minus 1, 1. So we already find that this matrix is singular. So it's singular, there exists an uncontrollable subsystem. Now, if we want to stabilize the system, well, first, of course, we need to check if the system is already stable or not. Okay, so we compute first the eigenvalues of the dynamic matrix A, so the determinant of lambda minus 1 lambda, so lambda square minus 1. So we have two eigenvalues, lambda 1 minus 1 and lambda 2 plus 1. And clearly the presence of this eigenvalue with positive real part means that the system is unstable. So next question is, can we stabilize the system through a state feedback? Okay, since we know that system S has an uncontrollable subsystem, being the rank of P equal to 1, smaller than 2, which is n. Since it has an uncontrollable subsystem, and we know that this uncontrollable subsystem cannot be altered by any input, so for sure not even a state feedback. So we need to understand if this uncontrollable subsystem is governed by the eigenvalue -1 or +1. We can proceed in different ways. So for example, we could check if the unstable eigenvalue, So check if lambda2 equal +1 is controllable or not. Because if it is controllable, since we know there's a one-dimensional subsystem which is uncontrollable, it means that lambda2 is, sorry, this is lambda1 is uncontrollable. The other one, but lambda1, since it's negative, it's already, this would mean that the uncontrollable subsystem is asymptotically stable. So even if we cannot alter its dynamics, it's already asymptotically stable. So it's not a problem from this point of view. If it is not controllable, then the system has an unstable, uncontrollable subsystem, and therefore S cannot be stabilized. There's nothing we can do about this. Okay? Well, how do we check if lambda2 is controllable? We can either check through the PBH test. So we would check the rank of A minus lambda2 identity matrix. We know that this matrix being lambda2 an eigenvalue is singular. So we would check if with B it would become of rank 2 or not. So this is an easy check. We can do this directly. So A is, where is it? 0, 1, 1, 0. Lambda2 is 1. So this means that we're looking at the rank of the matrix minus 1, 1, 1 minus 1, and the B matrix is 1 minus 1. So we see that there's only one linearly independent column, or if you prefer, the rank is equal to 1. So strictly less than 2. So lambda2 equal 1 is uncontrollable. And therefore, there's no way to stabilize this system. Just a note, if a system is not stabilizable through state feedback, for sure, it is not stabilizable through output feedback. So let me be more clear about this. Let's take this system here. in which we have found that there exists an unstable, uncontrollable subsystem. So we may have two ways of stabilizing the system. What we are looking at now is a state feedback. So we are saying that there exists no F such that the closed loop, let's call it 1, is asymptotically stable. And this is a state X. The output feedback is, instead, we take the output, and it's the usual feedback control that we have seen up to now. We may have here dynamic system, which is a controller. And so this closed loop system 2, which is different from the previous one, what we are saying is that if this is not possible, then there is no controller such that this closed loop system from the output is asymptotically stable. Okay, so this is something that should be clear, because sometimes in some exercise you may be asked, is the system stabilizable? And then you have some further information if you have the state which is measurable or not. And so you can reason on this. Why, let's say, not being stabilizable through state feedback is implies that it is not stabilizable through output feedback? Well, having the possibility of measuring the whole state is really much more than just having the possibility of measuring one linear combination of the state. So you can do more when you use feedback from the whole state with respect to what can be achieved through feedback from the output, which is a linear combination of the whole state. The other way to check if this lambda 2 is controllable is, of course, compute the decomposition with respect to controllability. Well, since we have found P, 1 minus 1 minus 1, 1, do this as, let's say, an exercise. We see that the image of P is generated by any vector which is parallel to minus 1, 1, for example. And so we know that there exists a change of coordinate which will decompose our system and put the uncontrollable subsystem in evidence. And this change of coordinates, we should use the let me choose the other one, which minus 1, sorry, 1 minus 1. This is the base of the image. And now we need to choose a second vector, which should be linearly independent from the previous one, so to obtain a t minus 1, which is invertible. So the easiest one we could choose is 0, 1, but there are, of course, many others which are possible. So with this change of coordinates, we would have t equal so something like this. Let's check. T minus 1t, we would have 1, 0, and then 0, 1. Okay, it works. And finally, we can compute a tilde as t inverse. So 1, 0, 1, 1, 0, 1, 1, 0 times t inverse. This is 0, 1, 1, 1 times t inverse, which is 1 minus 1, 0, 1. When we have minus 1, 0, 1, 1. Okay, so we look at this matrix in the new coordinates, and we know the structure that we are expecting from this matrix. We know that it should be block triangular. Okay, so if in a computation you do not obtain a 0 here or 0 matrix, it means that you did some wrong computation. Okay, so there are ways to check. And also, previously we have already seen that lambda 2 is uncontrollable. So this is the eigenvalue that we should expect here. This is the uncontrollable subsystem. Dynamics. And this is controllable. And again, we know that the original eigenvalues were +1 and -1. If here we find different eigenvalues, of course, it means that you made some errors in this computation. And similarly, when we compute b tilde, tb 1101 times 1 minus 1, we would have 1 and 0. So also here, if we do not obtain this 0 here, it means that we made an error. This is something we should expect in this decomposition. And okay, this decomposition is confirming the fact that we cannot stabilize this system since the uncontrollable subsystem is unstable. Okay. Well, you could try, easily imagine how this result can be used in practice. Let's take, for once, a physical example. Let's take a pendulum, okay, in which we have a motor, and you can command the motor. So this is your control input. Let's say this is an angle, and let's imagine that it's of mass m. So we in fact are deriving this model here as if the mass was all concentrated at the tip, and the length is L. So this determines, let's say, the inertia of this system. So in this situation, we already studied this when we studied the nonlinear systems. The inertia, which is ml square times the angular acceleration. And then we have the gravity effect, mgl sin theta, equal the applied torque. So this is a nonlinear system. But we know that we can approximate around an equilibrium point. And in particular, this system has two equilibrium points, zero angular position and velocity. So this is the, let's say, down configuration, or the upward steady position, so zero velocity and angular position equal to pi in this reference. So let's call this x xe2, okay, the second equilibrium point. And then we knew that the linear approximation so the linear approximation says around xe2, we found that the dynamic metric E2 was something like 0.1 G over L, and the input matrix was 0.1 over ML square. So we have this W dot equal AE2W plus BE2 U. And this is a linear approximation where W is a distance from the equilibrium point. So it's x, where x is the state theta and theta dot, as usual, x minus xe2. Well, so now we have a linear system. And when we compute the eigenvalues we have that PA2 of lambda square minus G over L. And so we have lambda 1 square root of G over L and lambda 2 minus square root of G over L. And obviously, the presence of this unstable with a real part strictly greater than 0 implies, unstable eigenvalue implies that xe2 is an unstable equilibrium point. For the nonlinear system. Well, this is the analysis that we did once for when we studied the stability of nonlinear system through the linear approximation. So now the question is, can we find a control such that the pendulum is kept at xe2 even in the presence of, let's say, disturbance, or in the presence of perturbations, where perturbations, we mean that they are limited in time. Well, we know that if I put my pendulum in this exact configuration, so at the equilibrium point, if there are no perturbations, the pendulum will stay there. What we are asking is something slightly different. I mean, really much more different is, imagine that for some reason the pendulum has been perturbed out of this equilibrium point, and we would like to swing this pendulum back towards its equilibrium. So we want to keep this pendulum in its upright position, which is an unstable configuration. Well, for now, since we are looking at the state feedback, we could ask, what if we use state feedback? So the question is it possible to find F such that with U equal Fw stabilizes the linear approximation? We know how to solve this problem, but before we proceed, I said, but be careful, here we are just talking about the linear approximation. Any questions? We are talking about the linear approximation. What we would like to achieve is a result on the original nonlinear system. So if such a feedback exists such that the linear approximation is asymptotically stable, it means that the linear closed loop is asymptotically stable. Well, this means that this is around xe2. This means that xe2 is locally asymptotically stable. So here the important part is locally. What does this mean? Well, this feedback, if it exists, and this is something we're going to see in a second, will be able to move back my pendulum from some initial configurations, even with non-zero initial velocity, up to some limit. Here I'm just showing these limitations in terms of angle, but of course, this is a limitation in terms of the state. Why? Because all this is going to be true, let's say, around the equilibrium point. So in the state space, if this is xe2, okay, this result will be true here, inside here. So this will define a basin of attraction. On let's say, of the linear controller of the nonlinear system. Okay, so the approximation is valid only in this Bayesian of attraction. So we are going to be able to stabilize with this linear approximation through this linear approximation approach only for initial conditions that are around that or belong to this Bayesian of attraction. So let's solve this problem now. Is it possible to stabilize this system through a state feedback, or at least the linear approximation? So, well, this is a controllability problem. So we can check the controllability of A to E, B to E. So the corresponding controllability metric is going to be 0, 1 over ml square, and AB is 1 over ml square, 0. And this matrix is non-singular. So, yes, there exists F, such that we can assign arbitrarily the eigenvalue lambda 1 desired and lambda 2 desired to AE2 plus B to EF. Let's call it 2. Well, this is a closed loop of the linear approximation. And therefore, we make the equilibrium point XE2 locally asymptotically stable. So physically, this means that we have our motor, we have the pendulum, okay? This motor is going to, for example, be through some current or some voltage, and we need the measurement, we need the state. In particular, we need the state W, which is theta minus pi, the equilibrium point, and theta dot. So you should know that theta can be obtained from an encoder. Typically, the motor has an encoder, and theta dot by a tachometer, which measures the angular velocity, or alternatively, numerically. From the encoder measurements. So this state feedback is going to be U equal some value F1 theta minus pi, some value F2, some constant, times theta dot. So the matrix F2 has the two components, F1, F2. Interestingly, this feedback law here is a PD type control law. Because we see that we have a proportional term F1 theta minus theta desired. Let's call this theta desired. And a derivative term, which is F2 theta dot. And so this is what you can achieve. Now, the last question you could ask yourself is, how would you choose F2, F1, F2? Well, we know that this can be achieved through the Ackermann formula. But this means that you should choose the desired eigenvalues, lambda 1 and lambda 2 desired. But therefore, the question becomes how to choose, or which are the best eigenvalues. Since we can assign any pair of eigenvalue, we could ask ourselves which are the best eigenvalues. Well, let's say that our past experience has taught us that there's nothing free, okay? Because we could say, well, we were going to choose these eigenvalues so that the closed loop dynamics is extremely fast, which means that there is a transient which disappears really, really fast. So we are, for example, going back to the vertical position in almost no time. But we know that there's a price to pay, and typically, if we look at this pendulum example, we understand that this will lead to some control effort problem. So this can also be seen that the further we move the eigenvalues from their original position, the larger the control effort or the control needed. So this is some one important point here. And how do we understand this? Well, we computed a formula initially in the old feedback, in the new coordinates before we got to the Ackermann formula. And this formula, we had some terms which were proportional to the difference between the coefficients so these were the F and then we had Z, okay? The coefficients of the original characteristic polynomial, and these are the coefficients to the desired polynomial. Well, it's not obvious, but the more these roots, the desired eigenvalues and the original eigenvalues are different, the larger, the further away are also these coefficients. Okay, so if lambda I is, let's say, desired is much smaller, in the sense it's going to be negative, then let's say the AI minus AI, it's not the same, let's say AK is going to be much greater than 1. Graphically, this means that imagine this is the complex plane. Imagine that these are the original eigenvalues, and these are the new eigenvalues, the desired ones. So we are moving this here, and maybe this here. Okay, so this distance, the larger is this distance, the larger is going to be the control effort. So again, the question is, which are the best eigenvalues? Well, there's a compromise, and this can be solved in an optimal way. There is an optimal solution. And this is a linear quadratic regulator, which solves minimum of the functional from 0 to infinity, x transpose qx plus, let's say, since it's single input, u squared times r in dt, where q and r are the weights just a couple of words. So you see, by choosing these weights, you give more importance to regulating to 0 or to the control effort. For example, if you choose R very large, it means that any small variation of the input is going to weight a lot in J. And so since you want to minimize this, you're going to do the minimum effort. Okay, so this is, you give big importance to the control effort and vice versa. So there's a solution. The solution of this problem when the system is controllable is a feedback. Let's say f star of x, where f star is a solution of some Riccati equation, etc. So there's an optimal solution with respect to this criteria. Okay, and this criteria, by choosing the weights Q and R, you decide what is important for you. Is it important to have a low consumption, low control effort, or to have a fast response to your problem? Okay, so that was a little digression. So you see how these simple concepts are really building up. We are just looking at a very small part. You can imagine that there's a whole, let's say, new world from here on how to stabilize with the state feedback, how to choose these gains, etc. As another remark, since we are on this sometimes, okay, there is a much easier solution in controlling a nonlinear system. Because up to now, what we know is we find an equilibrium point and we linearize around this equilibrium point. So the result in general is local. Whatever we're going to do on the linear approximation. And so the obtained performance, stability, whatever, is going to be local around that equilibrium point. But sometimes, let's again take this, our example. And square the pendulum. Well, the nonlinearity comes from this sine of theta here. This is what gives a nonlinear term. And we do not know how to treat this nonlinear term, how to solve any static or whatever kind of problems. But we see that if we choose the input tau as mgl sin theta plus v, what is the effect? So this is, let's say, a new input. When we apply this, the result is going to be ml squared theta tapu dot plus mgl sin theta equal mgl sin theta plus v. So the effect here is that we are canceling the nonlinearity. Okay. And how do we obtain this? Well, we obtain this through this control law. But this control law depends on theta. And theta is a state, or is one of the components of the state. So we could we could imagine that what we are doing is something like this. We measure the state we have now a nonlinear state feedback. And we have a new input V. And what we obtain is a new system which is linear. So this is this technique, which of course can be generalized, etc. Some very interesting condition. This is a feedback linearization. And the nice aspect when this is possible is that, of course, we obtain a linear system on which we can do all the reasoning, all the performance, etc. And it's a global result if this feedback linearization is possible. So, of course, is it always possible? Of course, this is not true. Unfortunately, no. And you also notice that to do in this specific case, we need to do this feedback linearization technique. We need to know exactly the model in particular. Here, we need to know exactly M, G, and L, and we need to have a very good feedback, etc. So it's not robust, let's say. If we have perturbations, we are not going to cancel exactly the nonlinearities. So, okay, so that was just a parenthesis. I will not ask this at the exam. It's just a curiosity to show that there are many, many other possibilities. Okay, let's go back and do another pair of exercises, just so that you are more into the exam mood. So let's consider the system -1, 0, 0, 2, 2, 1, 3, -1, 4. B, 0, -1, 1. Since we are just studying state feedback, the output is not involved, I'm not even given C. So the question is, what can we do? Can we stabilize the system or not, etc.? Well, first question is, of course, the eigenvalues of A. Well, the eigenvalues of A can be determined by noticing that these are the eigenvalues of the matrix -1 union the eigenvalues of the matrix 2, 1, -1, 4. And it turns out that the eigenvalues are clearly -1 and 3 and 3. So the system is unstable. Is it stabilizable through state feedback? Again, well, we now know how to proceed. Let's compute the controllability matrix. So 0, -1, 1, this is B. AB is again 0, -2 + 1, -1. 1 + 4 is 5. This is AB. And now we need to compute A²B as A times AB. So again, we have 0, -2 + 5, 3. And minus 1 plus 2021. Okay. Well, the presence of this row of zeros and the fact that we can find a minor of dimension 2, which is different from 0, so the determinant of this 2 by 2 matrix is non-zero, clearly implies that the rank of P is equal to 2, and it's strictly less than 3. So there exists a one-dimensional uncontrollable subsystem. So since the eigenvalues are -1, 3, and 3, we could proceed so we could check if -1 is controllable. Because what happens if -1 is controllable, since the uncontrollable subsystem has dimension 1, then let's say one of the 3 eigenvalue is uncontrollable. And so the system is not stabilizable. If -1 is uncontrollable, since again the dimension of the uncontrollable subsystem is 1, and therefore it's characterized by the eigenvalue -1, the 3 and 3 are controllable. And so the system is stabilizable. I mean, we could have said this directly here. The uncontrollable subsystem is asymptotically stable, so the system is stabilizable via state feedback. Okay, as an exercise, we could look for the decomposition just to, so that's a second alternative. The second alternative is necessary, at least if we need to stabilize the system when the system is stabilizable. So imagine that we have found the second result. So the question is, how do I find F? To do this, I need to decompose into a controllable and uncontrollable subsystem. I can stabilize the controllable part, and then I can go back in the original coordinates. So I need this decomposition. So I need to find T, change of coordinates, such that its inverse is image of P and completion. So we would have the image, well, we can choose the first 2 columns. They are linearly independent. So 0, -1, 1, 0, -1, 5. And then some other, for sure, one, and the simplest one is this one. So this could be a first choice, but oops, I finished. But once we obtain this T inverse, of course, if we had the possibility of using a computer, etc., or whatever, it would take longer to compute T and make all the calculations, which are therefore also more prone to errors. So could we choose a different T or T inverse? Well, if we look at the base of the image of P, so here we are saying that the image of P is generated by these two vectors, 0, -1, 1, 0, -1, 5, which is true, of course. But if we have x1, x2, and x3, we see that any vector that is generated by this base has the first component always equal to 0. So the space we are looking at is the plane x1, x2, x3, which means that what can be generated by 0, -1, 1, and 0, -5, 5 can also be generated by 0, 1, 0 and 0, 0, 1. To be really sure about this, it means that there exists A and B such that A times 0, -1, 1 plus B 0, -1, 5 is equal to 0, 1, 0. And similarly, there exists C and D non-zero such that, again, the linear combination of the old base would give the new vector 0, 0, 1. But there's no need to find these A, B, C, Ds, since I think here it's really, really obvious. So T minus 1 in this case could be really simplified into 0, 1, 0, 0, 0, 1, base of image of P, and 1, 0, 0. So in this case, it is even more evident to find the inverse of this matrix. So the first column should give, when we multiply T minus 1 by this first column, we should obtain 1, 0, 0. So this is exactly the third column. Okay, so clearly, like this, I'm picking the third column. The second column of T should be such that T minus 1 by the second column would give me, should give 0, 1, 0. So I should pick the first column of T minus 1. And finally, 0, 1, 0. So now I could compute A tilde, T A T minus 1. This is just pure computation, and I would obtain probably something that, not sure, probably you should check, something that looks like 2, 1, minus 1, 4, 2, 3, 0, 0, minus 1. And so we have confirmation that this is the uncontrollable part. This is the controllable part. We see that we have the zeros in the right place. Okay, so next step would be find F1 tilde such that the eigenvalues of 2, 1, minus 1, 4. This is A11 tilde. B, I didn't compute. Imagine we have B1 tilde here. F1 tilde, F2 tilde are some desired lambda 1 and lambda 2. Of course, since we want to stabilize with real part strictly less than 0, we find F1 and then we go back to the original. So F tilde would be F1 tilde 0. And in the original coordinates, we have F tilde T. So we find directly the F in the original coordinates, and that would close the exercise. Let me just do another example. Is it really different? I don't know. Let's just, they all look the same at the end. And you see how it's really an algorithm. Let's choose this, minus 2, 0, 3, 0, 0, 1, minus 1, 0, 2. 1, 0, 1. And the question is stabilize, if possible, through state feedback. Okay. B. Is it necessary we go through this? 1, 0, 1. 1, 1, minus 1 plus 2, 1, and 1, 1, 1 again. So clearly these two are linearly dependent. So while we can find a minor different from 0, determinant of a 2 by 2 submatrix, different from 0. So P is singular, and the rank of P is equal to 2, strictly less than 3. We can imagine that image of P, we would, for example, choose again the linearly independent columns, which would be like this, but these are, the subspace is also generated by, we see that we could simplify this by 1, 0, 1. If we subtract this vector to the second one, we would obtain a much simpler one, 0, 1, 0. So T minus 1, simple choice would be 0, 1, 0, 1, 0, 1, and then completion, for example, 0, 0, 1, and so on. Okay, so again, on this exercise, find f. Okay, you choose which eigenvalues to assign, etc. So we take a short break, and then we will probably start the second part of this lecture. Okay, any questions?
Io, professore, volevo chiederle, ma la cosa che abbiamo fatto prima, nell'esempio precedente, che praticamente abbiamo scelto come immagine di P e abbiamo trasformato i vettori che avevamo prima, diciamo, nella base canonica di R3, ma non si può fare sempre?
No.
Perché per esempio in questo caso non... Cioè perché in quel caso abbiamo trasformato nella base canonica?
Perché questo ci porta a una matrice T alla meno 1 molto più semplice e quindi i calcoli sono molto più semplici. È solo un fatto di convenienza di calcolo, ok? Non c'è nulla di più, però visto che in un esercizio è molto facile o perdere tempo perché i calcoli sono lunghi, oppure sbagliare perché i calcoli sono lunghi, tanto vale, se possibile, scegliere la strada più semplice.
Infatti c'è la base canonica, è quella che semplifica i calcoli, però
Sì,
non ho capito
per
perché...
esempio, here we do not have the canonical base. You see, there's nothing, it's simpler, okay? This choice here is simpler than the previous one, but it's not necessarily a canonical base.
Ok, perfetto, grazie mille.
Other questions?